Alright, so in this video we go over section 6.4, which is logarithmic functions. So we are going to look at the relationship between these type of functions and the exponential functions. And then we're going to look at finding the domain of a logarithmic function, how to graph them, how does the graphs look like, and evaluate logarithmic expressions. Okay, so first of all, we are going to define logarithms, and in order to understand how do we change an exponential statement into a logarithmic statement, and backwards a logarithmic statement into an exponential statement. So a logarithm of the on the base, or rather a logarithm to the logarithmic function to the base a, where a is a positive number and a is not -1. That's very important to consider, and it's denoted y equals log subscript a of x, and we read logarithmic function to the base a, or simply we can say log base a of x. Okay, let me write it down right here. Log base a of x. That's the most common way to uh, read this function. So y is logarithm to the base a of x. Either way, I prefer the shorter version. And we go and relate the logarithmic function in the exponential form using this statement. So y equals log base a of x if and only if a to the y equals x. Alright, so the domain of this function is only the positive values, no, not 0 or negative. Or we're going to look at this statement with example. It's going to make more sense. And we are going to have different type of logarithms. Logarithms of any base, a. We are going to have as well the natural log. The natural log, if we have the notation, the ln notation means logarithmus naturalis from Latin, and has the base e. Remember the number e that we looked in the previous section. So, and then we have the common logarithm. A common logarithm, you will know it's a common logarithm if you just see the word log. In other words, we don't have any subscript here. So when we don't have a subscript, this is understood to be base 10. Another way to express the natural log is by saying log base e of x, but this is not very commonly used. The one that we use is the ln form. Okay, but what are they? How do we work with them? Okay, so let's see. For example, if we want to find the logarithm of the number 100, so we are looking for a power whose what power of 10 equals 100. So in other words, what we have to say is write the number what power of 10 to what power equals 100, and in this case is 2. So log of 100 equals 2 because 10 to the second equals 100. If we wanted to evaluate log base 3 of 81, we are asking ourselves, so what power of 3 equals 81? In other words, 3 to what power equals 81? So in this case, 4. So log base 3 of 81 equals 4. All right. Log base 4 of 16. In other words, we're asking ourselves what power of 4 equals 16. So 4 to what power equals 16? That is 2. The same number 16, but now in base 2. Log base 2 of 16 is asking ourselves, we ask ourselves what power of 2 equals 16, which in this case will be 4. In general, when we see an expression like this, log base a of x equals y, what power of y, what power y of a equals x. In other words, a to what power equals x. So that's how we go to evaluate logarithmic expression. So let's see. We're going to change this exponential into a form. I'm going to leave this definition here so we can refer to it because we're going to use it more often than not. So in this case, we have some exponential. We're given an exponential. They're asking us to change that into logarithm. So we are going to write the word log. Okay, but what's the base? The subscript will be that of the base of the exponential, which in this case is a. And in this case of the number 4.3, and that equals 3, right? Because a to the third equals 4.3. A to the third equals 4.3. So 3 is the power I have to raise the value a in order to get 4.3. And in this case we have base e. I'm not going to write log base e. For the special number e we have ln. Alright, we have ln of n equals 3.4. In other words, the exponent goes to the right hand side of the equation and the number that was here or the quantity that was here has the ln operator. Alright, now we are going to do the reverse, which is convert logarithmic statements into exponential statements. So we're going to do this by having m raised to the power 4, which equals 8. Again, because the logarithm asks us what power, in this case the power 4, which raises the quantity m, equals the number 8. And in this case, notice we have ln, which is log base e, so we need to add e to the 4 equals x. So that's how we write exponential form from this logarithmic form. Alright, determining the domain of a logarithmic function. To find the domain of the function y equals log base a of u, set the argument greater than 0 and solve the inequality for the variable. Well, first of all, it would be a good idea to name the parts of the logarithmic function. Number 1, this is the logarithmic operator, that is the symbol u, like the symbol log rather. And then this tiny a, the symbol, this subscript is base, is the base of the logarithm. And last but not least, this u, which is the expression or the quantity inside of the log symbol, this is called the argument. All right, that's called the argument. All right, let's find the domain of this logarithmic function. So when it comes to finding the domain of a logarithmic function, it doesn't matter whether you have the ln, and it doesn't matter the base either. All we care is the argument here. So we set the argument x plus 3, set it greater than 0, and solve the inequality for x or whatever variable. For example, if we had a y, we would solve in terms of y. All right, so let's write this using interval notation. It goes from -3, all the way to infinity. Okay, so we're going to confirm this when we look at the graphs of this later in a couple of minutes. Of course, you might want to write this using interval notation as well. You may be asked either or both, so it's important again to be, you know, familiar with both types of notations. Now let's look at the next example. So in this case we have a log base 5 of 1 plus x over 1 minus x. Again, the log symbol and the subscript, which is the base of the log, doesn't intervene at all when it comes to finding the domain of the logarithmic function. All we care is to set 1 plus x over 1 minus x, set that greater than 0. We set the argument greater than 0. So in this case, one thing to keep in mind is we have a rational expression here. So there will be two numbers that we need to exclude from the domain, which in this case will be the number 1, because if x is 1, we're going to have 1 minus 1, which is 0. Now that we have the inequality, if you recall from the previous chapter, in order to solve inequalities, turn that into an equation and solve the equation to find critical numbers. So multiply both sides by 1 minus x. And cancel. We get x plus 1 in the numerator. Well, x plus 1 equals the 0, and x equals -1. So -1 is the other number that we need to exclude. So what are we going to do here? Well, I think I'm going to need more space. So I'm going to scratch this because I need space for the factors. Alright, so I have 1 plus x and 1 minus x. -1 and +1. So as usual, when we solve a rational inequality, select numbers in between that lie within each interval. So I'm going to choose -2, I'm going to choose 0, and I'm going to choose +2. So I'm going to evaluate -2 on these two factors. So 1 plus -2 is going to be a negative number. 1 minus -2, be careful because, let me write that down, 1 minus -2, doesn't that become a positive? 1 plus 3, which equals +4. Okay, let's evaluate it at 0. 1 plus 0 is positive, and 1 minus 0 is also positive. Let's evaluate it at 2. 1 plus 2 is positive, 1 minus 2 is negative. So what are we going to do next? What we do next is multiply the signs and get the final signs. The negative times positive, it's negative. The product of two positives is positive, and positive times a negative is negative. Alright, so going back to the original inequality, we're looking for greater than 0. So because we're looking for greater than 0, we're looking for the positive part of this number line that we shade here. In other words, the solution set, the domain of this logarithmic function will be -1 to 1 using interval notation, using set notation, x such that x is greater than -1 but less than +1. Alright, let's move on to the next page, the next topic here. Let's see. Graphing logarithmic function. So the graph of a logarithmic function is going to look like this. Well, first of all, let me finish filling the graph because here when I was printing the paper, it wasn't, I was running out of ink. Okay, so this is how the graph of a logarithmic function looks like. Let's look at some of its properties. So the graph has an x-intercept at 1, 0 point of reference. The graph has no y-intercept. Notice it never touches the y-axis. The graph increases slowly for large values of x. So at the beginning it grows very steeply and then it kind of slows down when it comes to increasing and approaches 0. Actually for inputs for that go from 0 and 1, we get negative values. Okay, those are the numbers from 0 to 1. See, the y values are negative. And as it approaches 0, as it gets 0 on the x direction, it goes to negative infinity. If we look at this function, the domain is 0 to infinity and the range includes all real numbers. That is negative infinity to positive infinity. So let's graph these functions, the ones that we have in here in the list. Let me just graph the ones. So here in these two Cartesian planes, I have y equals log of x. However, we're going to do translations in order to see what happens with this function. How does it move? One thing I didn't mention, by the way, this function log of x has a vertical asymptote, which corresponds to the y-axis. All right, so let's see. Originally, again, this function has a vertical asymptote, so your graphing calculator will never display this vertical asymptote when you graph this type of functions using your graphing calculator. So that's why it's very important to have a good knowledge of all these properties of the function. So when it comes to graphing one of these functions, we come up with a complete. Okay, so this minus 3 is x minus 3 inside of the parentheses. You might remember this. What do we do? Horizontal shifts add h units to the x coordinates. In other words, shifts to the right h units. So what am I going to do? I'm going to choose only key points, not all the points. For example, this point right here and this point right there. And I'm going to move it 1, 2, 3 units, 1, 2, 3 units. But that's not the only thing that shifts. We actually need to shift the vertical asymptote as well. It goes from 0 when we shifted 3 units. That's what I'm going to do here. And then I'm going to do a graph similar to the one in purple here, in pink. But notice how is shifted. So let's write the domain of this function. The domain, it's no longer be from 0 to infinity. The domain in this case will be, so this got shifted, it's going to start at 3 all the way to infinity. Okay, so a horizontal shift, in other words, changes the domain. For the range, yes, I know it looks flat. It looks like the range is going all the way to 2. However, maybe I needed to draw this way so it looks more like it's going up forever as well. So the range will be all real numbers. That is y such that y belongs to the set of all real numbers. Over here, the domain x such that x is greater than 3. Okay, so that's how we find the domain. And the x-intercept, again, it gets shifted. It's no longer 1, 0. That point became 4, 0. Or, well, if you use my MATLAB does not list x-intercept and y-intercept as order pairs. They just write the number. And the equation of, in this case, the vertical asymptote, I'm going to use the VA for short. That'll be x equals to 3. So when you do the homework, when it comes to graphing some of this, you will be asked all of this. Domain, range, the x-intercept, and the equation of the vertical asymptote, most likely. All right, let's look at another example, letter B, for this example 4. Now notice we have y equals log of x plus 2, but we don't have parentheses. This plus 2 is not inside of the parentheses the same way it was this negative 3 here. So in this case, we're going to have a vertical shift. So we're going to shift it up 2 units. So I'm going to grab key points. Like this point, I'm going to move it 1, 2 units. And this point 1, 2 units. Do I have anything interesting? I think that's about it. 2 units like this and like this. Notice in this case the shifting is vertical, so the vertical asymptote location, it's not going to change, it's going to stay there. So I'm going to do a dashed line with the same color in blue, just so you can see how it belongs to. And it goes all the way like this. So let's list the domain. Domain. In this case, see how it's going from 0 to infinity, which is in set notation x such that x greater than 0. The range, on the other hand, is all real numbers, negative infinity to infinity, or the fancy notation in set notation, y belongs to all real numbers. We have an x-intercept, which corresponds to the point. Well, in this case, we need to be very, very careful with the x-intercept. All right, so because in this case, because the graph shifted 2 units up, this will be 1, 0 will no longer be 1, 0. It's going to be a different number here. Okay. How are we going to find that x-intercept? Okay, I think I'm going to come back to this video later. I'm gonna go back to this page in a further video to show you how to find the x-intercept for this. Okay. And the vertical asymptote will be x equals to 0, which is the equation of the vertical line right here. All right. So, and by the way, this is going to be a very, very tiny number. See how this point got dragged to almost 0. All right. Okay, let's move on to the next topic. Now, the key point here, something you might want to observe, is how we are going to relate these functions to exponential functions. So what are we going to do next is to graph those pairs of functions in the same Cartesian plane. So what I'm going to do here is I'm going to use my graphing calculator, which I'm about to show you here. Where is it? It's right here. And I'm going to graph log x and 10 to the x in the same Cartesian plane. Okay, let me start it up. Okay, so we're gonna go to y equals, let me clear this, and the log button is going to be located here. So I'm gonna press log of simply x, and I'm going to close the parentheses here. And for y2, I'm going to type 10 to the x, but in order to get the 10 to the x, because notice it's in blue, you need to hit the second, then log, and that's 10 to the x power. So let's see what's going to happen once I graph these two functions together. Do you notice anything interesting here? Yes, if you answer, if you're thinking of some kind of symmetry about the diagonal line, which is this one right here, then you are right. These two functions are symmetric to y equals x. And from the previous sections, from the last week's material, you might remember that when you have two functions that are symmetric to the diagonal line y equals x, that means that they are inverses of each other. So the blue is the inverse of the red one, and the red one likewise is the inverse of the blue one. Let's repeat the exercise for ln and e to the x using the natural log and the natural exponential log. So I'm going to clear. So this will be ln x, and over here where I see the ln, I have the e to the x in blue, so that means I need to press second and then the ln to get the e to the x. And I'm going to hit graph here. And I'm going to have a similar situation. You know, the situation is similar. We have these two graphs to be symmetric with respect to the diagonal line y equals x, right? So what are we concluding from here? Well, let's go back to the properties to page 2 on section, I believe this was section 6.3, exponential functions. Okay, if you compare the properties of both of these functions, okay, let me put this together. So the logarithmic function has an x-intercept but no y-intercept. The exponential function, on the other hand, has a y-intercept but doesn't have an x-intercept. See how those properties are inverted? Now, the domain of the logarithmic function is all positive numbers, and the range is all negative, all the real numbers, rather. As opposed to the domain of the exponential function is all real numbers, but its range is only the positive numbers. See how those two properties are just reversed or interchanged? That's because a function and its inverse share all those properties. So if you will, for example, let me go back to the back of this page to write something pretty interesting. So in this case, when it comes to inverse functions, the domain of f of x is the same, well, is the range of the inverse function, and vice versa. And then the domain of f inverse is the range of f of x. All right. So for example, if I have f of x and f inverse of x, so if I input whatever value x, that's the domain, it's going to have a range. But that range is going to be the inverse function's domain. And then if I input that domain, that range that came from the original function, its range will be again the same input as the original function. So that's why they call it, that's why they are inverse functions, inverse of one another. All right, so let's use that fact in order to find the inverse of an exponent of logarithmic functions and the inverse of an exponential function. So first of all, recall that in order to find the inverse function, change the f of x notation to that of y notation. Y equals 3 log x minus 1. And I think I wrote a double equal sign. Let me erase it. Okay. And well, and then the first step in order to find, the next step to find the inverse function is to interchange x's and y's. And then solve the equation for y. Now, let's see. First of all, I need to isolate the logarithmic term by dividing both sides by 3. So boom, boom, they cancel, and I get log of y minus 1 equals x divided by 3. If we recall, let me write down the property at the top. The connection between logarithmic functions, log base a of x equals y if and only if a to the y equals x. So in this case, our x is the y plus 1 and the x over 3 is our y. So I'm going to write the base, which is a. However, when we don't have anything, when anything in the subscript, it's supposed to be a 10. I'm going to write it this time only just so you can see where it's coming from and what it means. So in this case, I'm going to write this in exponential function. It's going to be the base of the log raised to the right hand side, which is x plus 3, 10 to the x over 3, and that's going to be equals to the argument of y, which is x. Okay, so in this case is y minus 1. And all we need to do here is to add 1 to both sides to get y by itself. And finally, before we call this a final answer, keep in mind that this y is now renamed f inverse of x. All right. And this is final answer for this exercise. Let's do another example. G of x equals ln of x plus 4 minus 5. First of all, change the g of x for a y. Okay. And then interchange x's with y's. And then let's try to solve for y by first adding a 5. And then ln y plus 4 equals x plus 5. And then go from logarithmic form to exponential form. In this case, this ln implies a base. The a is a letter e, the order's number, letter e, the base e. So e to the x plus 5 equals y plus 4. And finally, all we do is subtract 4 to both sides to get y equals e to the x plus 5 minus 4. And let's do the last example. Oh, wait a minute. This is not the final answer. Careful. The final answer must be in the notation of the inverse function. Rather, this is not f, this is g inverse. And this is the same, e to the x plus 5 minus 4. Let's do our last example, in which first we change y equals 4 to the x minus 5 plus 3. And then we interchange x's with y's. Be sure that when writing these expressions, this y plus 5, for example, this x minus 5, looks like the power of 4, all right? So let's solve for y. So 4y minus 5 equals x minus 3. And now in order to change this, we're going to go this way. We're going to change from the exponential statement into a logarithmic statement. So in this case, the base is 4. That means we are going to have a logarithm of base 4 of the quantity x minus 3. And we just carry this y minus 5. So all we do is add 5 to both sides, and y equals log base 4 of x minus 3 plus 5, which is f inverse in function notation. And this is final answer for this one. Alright, so the next and last topic for this section is not graphing, but rather evaluating logarithmic functions. Okay, so now that we found out that exponential functions and logarithmic functions are inverse functions to one another. All right, so now that's the main takeaway of this section. So what do we mean? For example, if we have 3x equals 6, for example, in order to solve this equation, we do the inverse of multiplying by 3, which is to divide by 3. That's going to give us x equals 2. When we have the square root of x equals 5, to get that to get x by itself, we would do the inverse of taking the radical, or taking the square root, which in this case is to square both sides. That's going to give us x equals 5 squared, which is 25. All right. X minus 4 equals 3. The inverse of subtracting 4 is to add 4. That's going to give us x equals 7 in this case. So when it comes to logarithmic and exponential expressions, we have a similar way of thinking. So the logarithm with the same base as that of the exponential, pretty much this logarithm and this where is my other pen? Oh, this logarithm base a cancels the exponential base a, and likewise a raised to a log of the same base cancel each other and leaves us with x only. So now let's see this in action with some examples. All right, so when we look at the definition of log base 8 of 64, so we were looking for the power of 8 that gives us 64. And in this case, well, with a simple statement or a simple exercise like this, it's easy to just do it by hand. Well, that's the answer is 2. because 8 to the second, which is 8 times 8, that equals 64. But now we're going to take a different approach into evaluating these types of expressions. Okay, so if possible, well, and in this case, in this sequence of exercises, it will be possible for all of them, by the way. We are going to try and write the number that we want to evaluate, which is in this case the number 64, as a power of 8. What do we mean? So for example, log base 8, can we write the number 64 as a power of 8? If so, what would be that power? Well, 8 squared. All right. So we are going to use the first property, log base a of the exponential a to the x, and cancel each other. So log base 8 cancels this 8, and this equals to 2. And if you want to stick with the definition, this is because 2 to the 8 to the second rather equals 64. Okay. Let's see, we have log base 6 of 1 over 36. Here, notice how the 36 is a power of 6. However, in this case, we need to do a little bit of work before we can get that done. What do we mean by that? Well, first I'm going to move this 36 to the numerator with negative exponent. 1 over 36 is the same as 36 to the negative 1. Now let's work with the number 36. And it turns out that the number 36 is a perfect power of 6. That is 6 to the second power. But don't forget, this is raised to the negative 1. All right? Now, by the multiplication property of exponents, that is, when we have a to the m to the n, these two powers multiply each other. That is, a to the mn. We're going to do this in this case. We're going to multiply 2 times negative 1, which is negative 2. And now notice how we have this exponential and log with the same base. So now we are ready to cancel this out. And our final answer is negative 2. All right. Let's look at the next example on the next page. So log base 9 of 1. In this case is 0 because log of 1, regardless of the base, log of 1 is 0. Doesn't matter if you have log base 7 of 1, log base 13 of 1, and well, how do we justify this? That is because, well, if we write this, a to the 0 equals 1. In other words, 9 to what power equals 1? And any number, like the number 9 to the 0 power, will be 1. If it were log base 7, 7 to the 0 power equals 1. Whatever base raised to the 0 power is always 1. All right? Now let's evaluate this one, log base 3 of 9 to the negative 1. And in this case, if you look at the numbers, the first thing you do is see if there is a relation power-wise. For example, the number 9 can be written as a power of 3. And that's what I'm going to do. Log base 3 of 3 squared. But don't forget that this 3 squared, which is 9, is raised to the negative 1. And then I'm going to multiply these two powers, 2 and negative 1, just the same way we did it in the previous example. And now observe this. Use a different color instead. How about that? Now, the base of the log is now the same as that of the exponential, so we may just cancel these two. So our final answer to this equals to -2. All right, so the next one, e to the ln of 3. Okay, so in this case we have the other property going on, which is the second one. E to the ln, that's the same as 8 raised to the log base a, which is the second statement right here. All right, this ln, I'm gonna do this only once, but just so this is clear, this is the same as saying e to the log base e. So in this case, notice how the base of the log matches the base of the exponential. So in this case, we're just good to go and cancel this log and this e. And this is 3. Just the same way we can simply cancel e to the ln. This is what we are going to be doing for the rest of the chapter, but I did this only once just so you can see why these two can be just canceled like that. And by the way, there was a little typo here. It's not going to be on your PDF. And just the same way, e to the ln cancel, ln of e cancels for the same reason, because ln, which can be written as log base e of e cubed. So the base of the exponential matches that of the logarithmic operator, so boom, boom, cancel, and this is also 3. Okay. I think it is more visual when we look at letter G. 2 to the log base 2. All we do is boom, boom, cancel these two, and this is x minus 5, whatever remains, which in this case is x minus 5. 10 to the log. We can just go boom, boom right here, because in this case the log doesn't have any subscript. And again, recall that when we have no subscript for the log operator, it should be understood that the base is 10. So final answer, whatever it remains, which in this case is 3x minus 11. All right. Now let's look at this nested collection of logarithms and exponentials. And yes, looks huge, looks ugly, I agree. But we're going to do one pair at a time. Okay, I'm going to observe this log base 13 of 13 to this humongous mess. All I care is that this log has the same base as this exponential. So those go away and I'm going to be left only with log base 13 of 13 to the x to the 13. Okay. And then the next thing I notice here is that this base, which is 13, matches that of the base. So these go away a second time. And we are left with x to the 13. And that's final answer. What about the last of two? Okay, so log of the cube root of 100. Well, that's interesting because we have that cube root. We need to get rid of that cube root using the properties of radicals. Recall that when we have some the nth root of a, that's the same as saying a to the 1 over n. Well, there's more if you care about the n, but in this case, let me keep it simple for n only. So this is the same as saying log base Well, log base 10. In this case, we don't have to say log base 10. When we just say the word log, it will be also understood that it's log base 10. Okay, unless it's another type of log or a base with another base, a log with another base, like log base 7, log base 5, log base 4. Well, in that case, we specify the base. But when we mention the word log, that's only base 10. So that's log of 100 to the 1/3. Okay, so why not? I'm gonna write the invisible base, which is 10. The number 100 can be indeed written in as a power of 10. That is log base 10. I'm not gonna write the 10 again, just previous time. This is 10 squared. 10 squared is 100. But don't forget about this 1/3 over here. All right. And then again, by the power of another power property, or one of the laws of exponents rather, we multiply these two powers. So 2 times 1/3, that's simply 2/3. And this is where log and 10 cancel each other. And final answer, 2/3. All right. And let's do the last of them. Log base square root of 3 of 9. Well, this base is a little bit weird. Okay, this will require a little bit more of work than the usual. All right, so let's see how is this going to work, by the way. All right, so let's see. Well, notice the base involves the number 3, but not just the number 3, but rather the square root of 3. But if we didn't have the square root of 3, we would just work with 9, because the number 9, it's a power of 3. We are still going to do that. I'm going to go like log base square root of 3 of 9, which is 3 squared. All right. And then, okay, here is where things might be a little bit tricky. So my goal is to write the number 3 and make it match with the base of the log. So how are we going to do that? First of all, well, here I'm not going to do anything really interesting. Hopefully, in fact, if you think of this, it's like pretty obvious and possibly even unnecessary. All right, possibly even unnecessary, but in this case, adding this parenthesis here, that's going to be a game changer when it comes to write these 3 in terms of a radical. All right, so what are we going to have here? Well, let's see. So somehow I need to turn these 3 into square root of 3. So this square root of 3, let me write it on the side, is the same as 3 to the 1/2. All right. So somehow I wish I had a 1/2 in here. All right. And guess what? Curiously here, I can just add that 1/2 provided I added something else. So I'm going to add a 1/2, the 1/2 I'm missing, but I'm going to multiply that by 2. Because 2 divided by 2 is 1, which is the 3 to the 1 that I had originally. Okay, let me erase this again. I know I'm erasing once and twice, so in other words, what I need here is to have a special version of 1. Okay, I'm going to turn this number 1 into into 2/2 squared. Do we all agree that 2 divided by 2 equals 1? Okay, the denominator of the exponent, I will use it in order to write this, come up with this radical. So first of all, I'm going to decompose these two halves, and I'm going to write it as 3 to the 1/2 times 2. And then that whole thing raised to the second power. All right. Now there's one thing that we need to observe. Let me highlight this 3 to the 1/2. That's going to be turned into, this guy right here will be turned into the square root of 3, which is finally going to match over there. All right, so log base square root of 3 will be the square root of 3 squared, which is this square came from these two that remain there, and then that squared. And then again, the power of another power will be log base 3 of square root of 3, 2 times 2 to the 4th power. And after some magic with numbers here, we'll guess what? These two bases match, which means that we are ready to cancel this out, and final answer is 4. And this is a good moment to quit, so I will see you on the next video.